Hi, hello, dear students. Welcome to my second lecture on coordination chemistry. In this lecture, I would like to explain the topic ligand chemistry, or you can also call it is ligand chemistry. Most of you already identified what is ligand in the first lecture. Once again, we will see the in-depth of this ligand and their classification and their tendency. Not only that one, how these ligands are going to impart stability to the coordination complexes also. First of all, I would like to tell what is a ligand. Ligand is a neutral molecule or anion or a cation. Ligand is a neutral molecule or anion or a cation. So this may be a molecule. Molecule means you all know it is a neutral one, or it may be anion, or it may be a cation. So ligand may be a neutral molecule, or this may be a cation or anion, which are actually directly linked to the central metal, atom or ion in a complex, that is called as ligand. So these anion and cation are said to be directly linked to central metal, atom or ion are called as ligands, So it's the definition of ligand we have already observed in the first lecture. Once again I have recollected the information for you, that is a neutral molecule or an anion or a cation which is directly linked with the central metal atom or ion in a complex. Moving on to the important point of ligands, these ligands are said to be attached to central metal through what kind of bond? The kind of bond is called as coordinate covalent bond between this metal and ligand. What is the bond is present? The bond present is called as coordinate bond, or you can say coordinate covalent bond, or you can also call this one as day-2 bond. So ligands are said to be linked with the central metal via a type of chemical bond which is called as coordinate covalent bond or day-2 bond. Actually, there are few exemptions are there in this. There are some molecules are there in ligands which have which also called as molecules which possess some free electrons with them, means some lone pair of electrons in the molecules of ligands over a central atom remains unbonded. Such cases are there, means those ligands can be understood easily by the formation of coordinate covalent bond. So they will help the coordinate covalent bond easily when a electron pair minimum is present on the central atom of the ligand. For example, if you take nitrogen and ammonia, it is having a lone pair of electron on this nitrogen atom. Why we are calling lone pair is nothing but it is unbonded pair of electrons. This is electron rich species. These electrons can be donated to the central metal in the complex, making this ammonia is a very good ligand in the complex. So ammonia is an example, is a free ligand which has one lone pair of electron that is said to be engaged in bonding with the metal in complexes. Similarly, in the similar fashion, we will have water is also an example. In water, we have oxygen is the central atom which has a capacity of 2 lone pairs, but we require only 1 lone pair with the metal with from this water, making a day 2 bond with the metal and oxygen. So, one atom must be there in a ligand molecule which possess some electron pairs which are unbonded, required for the formation of coordinate covalent bond or day 2 bond in the complexes. Moving on to the different kinds of examples, we have Cn minus is there. Cn minus means cyanide, carbon, nitrogen, there is a triple bond is existed in that one, and you have carbon lone pair is there, and nitrogen also will be having a lone pair, Cn minus is there, and this is also a ligand, a negatively charged ligand is there. Likewise, we have Cl minus is there, the 4 lone pairs are there, this is also a ligand. That means ligand may be molecule or an anion or a cation which is directly linked with the central metal atom or ion in the complexes to make the complex stable. So, in this discussion, what we have noticed is the lone pair is contributed by the ligand atom to the central metal, means ligand will behave like a donor species, and central metal, as you all know, it is accepting, it is called as acceptor in this day 2 bond, means which is donor, that is called as ligand, which is electron rich species which is donating lone pair of electrons to the central metal in this complexes. As I said earlier, acceptors are nothing but Lewis acids, they will behave like Lewis acids, but in this ligand chemistry we have to notice that ligands are also behaves like Lewis bases. What is Lewis base means? In complexes, ligands will behave like Lewis bases, as they have electrons required for day 2 bond with the central metal. So, one will completely donate the pair of electrons to other in this coordinate covalent bond. So, the ligands are inviting the central metal to participate in the coordinate covalent bond. It is also equal sharing of pair of electrons between the atoms concept, but the sharing is only happens from this ligand side only, means one is acceptor, another one is donor. A little different version of covalent bond is coordinate bond or day 2 bond. Moving on to the important versions of this ligands concepts, we will see that now. Suppose when you are expecting something from ligands, the formation of these complexes also actually takes place in 2 different things. In this, ligands are said to be having a lone pair of electrons which can be donated to the central metal atom is one condition. For formation of complexes, we have some conditions. So, formation of complex involves the one point what we have noticed is nothing but ligands should have lone pair of or pairs of electrons. Ligands should have pair of electrons, or you can say pairs of electrons to be donated to the central metal atom, to be donated to the central metal atom. central metal atom in the complexes. So to form a complex, ligand should have pair of electrons to be donated to the central metal atom is one of the important point to be noticed. The another point is nothing but the central metal, whatever is there, the central metal or whatever the metal ion is there, that should have some empty orbitals to accommodate that electrons donated by ligands. So we can say central metal or ion should have vacant, or you can say available vacant orbitals, that orbitals must be having some equal energy with equivalent energy to accept the electron pairs. So definitely here what we have noticed is a very important point. First electron rich species is ligand is there, that is capable of donating electrons, but at the same time central metal is there, the central metal atom or ion is there, that must be capable of accepting the electrons by means of providing some vacant orbitals with some equal energy, which accommodation of electron is required. So that must be there to form a complexes. In all these things we have understand that the central metal whatever is there, these conditions are said to be fulfilled by particular metal atoms. In our discussion they are called as transition metals. Transition metals are said to be fulfilling the needs of formation of complexes. Means the characteristic property of transition metals is formation of complexes. So transition metals definitely will fulfill the needs of the formation of complexes, and they will behave like central metals, will provide a vacant orbitals to accept the electrons from ligands during the formation of complexes. So these are the two important points you must remember in the ligand chemistry complex compounds. Okay, we will see some other things also in this discussion. So what else we have to discuss here is most of the reactions are there in the complex compounds. These metal atoms or ions are there, they are said to be giving some kind of reactions in which aqueous solutions will take place. In the aqueous solutions there is a chance of the replacement of one ligand with another ligand by changing the physical property like color. Let us observe, we have a cobalt, complex is there like CO, H2O 6 times 2 plus. Let us suppose this is a complex which is believed to be giving a kind of color, but that color is going to be changed when we change the ligands. That is one example we can understand. Not only that one, when we have nickel complexes are there, nickel complexes like Ni H2O 6 times 2 plus. These complexes are said to be also changing their color in aqueous solution when we have promoted ammonia in the case of in place of water. So what will happen? All the water molecules are replacing with the ammonia, then the idea will become Ni NH3 Ni NH3 6 times 2 plus. Here what we have noticed is nothing but in this aqueous solutions the color changes from green to blue. So, this is green in color, this is blue in color. So, what we have observed is nothing but these reactions in aqueous solution are actually the reactions of complex compounds in which the metal is said to be attached with the number of water molecules. Here the number of water molecules linked with nickel are 6, and these water molecules in aqueous solution we have noticed, but once the color changed when we change the ligands indicates that the molecules have predominantly attached to the ammonia molecules will displace the water molecules, means the preference of this ligand with the metal also is an important one to make the ligand stable and also changes the physical properties in the ligand chemistry. So, ligand changes, physical property also changes, stability of the molecule also changes. This is a simple idea to understand this ligand chemistry. So, here and here in the both the cases we have ligands, water and ammonia both are this monodentate ligand. So, I am talking about monodentate. What do you mean by that one? Is nothing but one pair of electron donated by the water or ammonia in the nickel complexes to make a change in the physical properties. So, now let us see what are the different kinds of ligands on the basis of the number of electron pairs donated to the central metal. Now, I am going to talk about types of ligands. Types of ligands. In the first case, I am talking about monodentate ligands. Monodentate ligands. In the name itself, it is very clear that they have one donor atom and they only donate one pair of electron to the central metal is the meaning of this discussion. Okay. So, here they will donate one electron pair using one donor atom, So, donor atom is one and that will donate one electron pair to the central metal atom, or ion. We have observed that F minus, Cl minus, Br minus, H2O, NH3, even that negatively charged Cn minus, NO2 minus, OH minus, CO, etc., etc. So, these are all an example of this kind of this ligands. So, ligands examples we observed. In this we do not have any doubt, but here we have more atoms are there. In this the donor atom is oxygen, in this NH3 donor atom is nitrogen. In this Cn we have a donor atom maybe of either nitrogen or carbon, In this NO2 again we have the same kind of suspicion. In this NO2 we have different kinds of things are there. In this we have either oxygen or nitrogen. Here we have oxygen is the donor atom, Here we have oxygen is the donor atom, etc. So donor atoms are must be important. So any one atom in the ligand, if it behaves like a donor atom, then that can donate only one electron pair to the central metal to say that this ligand is behaving like a monodentate ligand. Okay. Let us talk about bidentate ligands. The next one, bidentate ligands. The next one is bidentate ligands. Bidentate ligands. In the name itself, we are saying that these are bidentate ligands. Means ligands are there which have two donor atoms. Earlier we told one donor atom in the case of monodentate ligands. Now we have to say that they have two donor atoms. They have two donor atoms, means they will donate two electron pairs. They have ability to link with the central metal atom via two donor atoms. Two donor atoms definitely must be there with these ligands. They have also saying that ability to link with the two donor atoms, ability to link with the central metal atom or ion. Means that linkage itself is coordinate covalent bond, and this coordinate covalent bond is possible with bidentate ligands with two bonds. As I said earlier, ethylene diamine is an example. Ethane 1,2 diene or ethylene diamine is the best example for this kind. So we have the structure is like this: CH2, here this one nitrogen of amino group is a donor, this is another donor. So two nitrogen atoms are there. So this is in this way, these two donor atoms of nitrogens of this ethylene diamine capable of making this ethylene diamine bidentate ligand. Another example we have oxalate. Oxalate is there, OX is the shortcut lettering in this. Oxalate also you can able to see such type of things here. O minus, this is minus, this is minus. These oxygen atoms, two oxygen atoms are there, same type are there. Here two nitrogen atoms are there, same type of are there, same type are there. Here also same type of two oxygen atoms are there. They are also behaving like donor atoms to make this oxalate ion a bidentate ion. Not only that one, we have glycinate as an example. Glycine amino acid is there. From that glycinate formed. GLY is the notation, and in this we have carboxylic acid group 1 CH3 CH2 COO O minus. This one oxygen is behaving like one donor atom. Another one we have NH2 amino group. This is one donor atom. So here the two donor atoms are there, but these two donor atoms in this structure are different atoms. Here two oxygen atoms in oxalate are same. Here two nitrogen atoms in ethylene are same. So what we noticed is in bidentate ligands we have a identification, we have a different kind of idea, that is bidentate ligands in which the coordinating groups are same, or called as symmetrical ligands. Means coordinating groups nitrogens are there, they are same. Here nitrogen oxygen is there, they are different. So those are having same coordination, what we call coordinating groups are there, they are called as symmetrical bidentate ligands. So we can call these two are symmetrical bidentate ligands. But here what we noticed is different are there, so that we can call as unsymmetrical bidentate ligand. This we can say unsymmetrical bidentate ligand, unsymmetrical bidentate ligand. So keep in mind that bidentate ligands can be divided into two types. The one type is called as symmetrical bidentate ligand, another one is called as unsymmetrical bidentate ligand. Now, next we are going to see tridentate ligands. Third one, tridentate ligands. As I said earlier, we are told monodentate, we have told they are bidentate. Likewise, now we are saying they are tridentate, means just we have to put 3 here, that is the ligands are there which have 3 donor atoms which are called as tridentate ligands. So let me give the examples also. So in this tridentate ligands, we have an example is there, that I can say diene. The shortcut is diene, that is a diethylene triamine. Diethylene triamine. This is diene, means nitrogen atoms are there, NH2 type, 3 types are should be there. But in this, ethylene means C2H4, you all know very well that CH2 groups are there. This CH2 groups, 2 groups are there. In between them, CH2 groups, we have one amino group is there. So NH group is there. So these CH2 groups, whatever CH2 groups are there, these CH2 groups join with the NH2 groups like this, and this is a donor, this is one donor, this nitrogen is another donor. So total of how many donor atoms are there, means 3 donor atoms are there in diethylene triamine. In place of this diethylene triamine, if they ask any other thing, that we will call it as another example, best example, that is terpyridine. So this terpyridine shortcut is terpy, means whatever pyridine is there, we have, you know, pyridine structure will be like this. Nitrogen is the donor atom. Such type of rings, 3 rings we have to write, keeping nitrogen atoms are donor atoms in the structure. So for that, I am going to write one pyridine here. This is nitrogen, a donor atom, and here one I am attaching the pyridine rings. Here one nitrogen I am attaching, here one nitrogen I am attaching. So these nitrogen atoms behaves like donor atoms in terpyridine. That's why we will say it is also comes under tridentate ligands. Tridentate ligand is over. Next, we are going to see tetradentate ligands. Fourth one, tetradentate ligands. Tetradentate ligands. Here we can keep 4. So 4 donor atoms must be there, and in the case these possess 4 donor atoms, you all know. The example for this one is little differently is given to us, which is nitriloacetate. One example, nitriloacetate. Nitriloacetate means this you can understand that this nitrogen atom itself is a donor atom in the structure. At the same time, this is having 3 CH2COO groups, acetate groups, CH2, COO minus groups, CH2COO minus groups, here CH2COO minus. Like that, we have to say that this is a tetradentate ligand. This is one best example for the tetradentate ligands. Not only that one, we have a triene is there, another example, that is triethylene tetraamine. We can say this is triene, shortcut is triene, triethylene tetraamine. Triethylene tetraamine means in the name itself, ethylene groups are 3 groups must be there, and amines group must be 4 must be there. So in such a way we can write CH2 groups are there, they are CH2 times comes, that we are writing CH2 twice we are writing, and I am keeping one NH here, and again I am taking one more CH2 twice, again I am writing one NH, next I am taking CH2 twice. Okay, already 2 NH2 groups came, so we have to attach a 2 NH2 to make it is tetradentate ligand. So to make it tetradentate ligand, we have to keep it 4 such type of donor atoms. So donor atoms must be 4 in the discussion. So 4 means tetradentate ligand. 4 donor atoms means tetradentate ligands. Similarly, we can say pentadentate and hexadentate also, but important kind of the ligand is hexadentate ligand, EDTA. That's what we have observed in the last class also. Okay, this is about tetradentate ligand. So let us talk about one special kind of ligand concept. That is chelating ligand. Chelating ligand. Ligand or ligands. Chelating ligand or ligands. So chelating ligands, how this concept actually came into discussion is nothing but, actually what we discussed about the bidentate ligands, or some other polydentate ligands, that bidentate or polydentate ligands themselves called as chelating ligands in a coordination complex, because they form some closed or cyclic ring type of structures. They form closed or cyclic ring type structures. So either bidentate ligand or polydentate ligands are there in the ligand complex compounds. They must create some cyclic ring type of structure to say that that type of ligands are called as chelating ligands. Means those complexes are called chelates and these ligands are called as chelating ligands. Here the word chelate is there is a Greek letter which means claw. Okay. The complex formed by some of the examples like copper complex, if you take, copper is there with a bidentate ligand, ethylene diamine only I have taken, CuEn twice, 2 times I have taken, and in this copper complex ion the ethylene diamine is there. Ethylene diamine is said to be making a cyclic ring type, closed ring type of structure with the central metal copper. You can observe the structure now. So even though ethylene diamine is a bidentate ligand, it is forming a closed cyclic ring type of structure in the copper complex. To make this complex is chelate, and this ligand is called as chelating ligand. So what is chelate? What is chelating ligand? Chelate is a stable complex and these ligands are called as chelating ligands. They form closed or cyclic ring type of structures. So what is the importance of this type of chelating structures, you can ask? Means these chelating structures may have some ring type of structures where we have 5 membered here, including this copper. This ring is formed with the 5 atoms, means 1, 2, 3, 4, 5. So it may be 5 membered, or sometimes the chelating complexes may contain around 6 membered rings also. Completely they are more stable. So these ring structures are said to be giving stability to the complex compounds. That is one point. The other point is nothing but these ligands are there, they are larger groups for more unstable. So ligands with larger groups are there, they are unstable. Smaller groups are there, they are stable. In the discussion, the reason is like in organic chemistry we used to talk about steric hindrance. Here also the same thing will be applicable. So chelating ligands do not contain any kind of unsaturated groups, means here there is no double bond formation, complexes are there in the ligands. Do remember, chelating ligands are more stable. So finally the concept of chelates is giving as extra stability to the complex compounds, in which copper, nickel, magnesium, aluminum, these all tends to form chelating complexes, and they are also colored complexes also, you can say, by means of again their stability. And also sometimes what we will do is these chelating complexes will be used as water softeners, and the separation of lanthanides, anthonides also possible with this type of complexes uses in the chemistry. Many food preservation complexes are there. Now many importance of these complexes in the solvent extraction, and as usual we are talking about the water, elimination of harmful radioactive materials from our body. We can use the complex hexadentate complex EDTA. These are all said to be the most important chelating ligands containing chelating complexes. So, purpose of study of chelating ligands is making them stable, and many other applications or the important features are there, applications are there for the chelating ligands in the chemistry, to say ligand chemistry has got a significance in our subject. Okay. Finally, I am going to give you another important definition of ligands, that is type of ligands, that is called as ambidentate ligand. The ligand's name is nothing but ambidentate ligands. I am going to talk the most important point in the examination point of view, that is ambidentate ligand, because some of the ligands are there, some ligands which have two or more atoms are there forming complexes with the central metal atom. But in these ligands we have a possibility of donating via either any of the atom. Means, for example, if you take metal with NO2 linkage, nitro, okay, so nitrogen is the donor atom. In the same way, if this is noticed as metal with oxygen linkage with the same formula, so isomerism in the ligands making them ambidentate ligands. This is nitro, this is nitroso, but as per the IUPAC nomenclature, you must say this is nitrito. So first one you will call it as nitro, this one you will call it as nitrito. In the same way, if you see metal with the cyanide linkage, carbon is the donor atom, where you will call it as cyano. Cyan is cyano, we have donor atom is carbon. If you write this one is NC, metal with nitrogen as the donor atom with same molecular formula, this we will call it as isocyano. Okay, so formula is same, but the donor atom is different. Such kind of ligands are called ambidentate ligands. In the same way, we have metal with thiocyanide, SCN, whereas this SCN is thiocyanide, sulfur is the donor atom. If you just change it with nitrogen, then this will be metal with NCS. This is again isomerism, isothiocyanide. So now you observed the differences in these ligands. So what is ambidentate ligand? Means two or more donor atoms may be there, forming complexes, only one donor atom is attached. So here more than two, so your two donor atoms are there, nitrogen is there, oxygen is there, but formation of complex takes place via only one donor atom. So ligands with two or more donor atoms but attached with metal by only one donor atom. So we have availability of two donor atoms, but to form a complex, these ligands will make use of one donor atom only. such are called as ambidentate ligands. In the same fashion, when you are talking about polydentate ligands, those type of polydentate ligands are said to be having a flexidentate characteristic is there necessary to study in the ligand chemistry. So, this is what we have in our present session, talking about ligand chemistry, different types of ligands with examples, and ligand chemistry, how makes the complex compound more stable, all we observed in this session. I hope you understand this session. So, we will see in the next session with more and important points in the coordination chemistry. Have a nice day. Thank you.